And I want to start with something I found literally last night on Instagram. I thought this might be a bit of an encouragement for you. Well, there's Miss Gracie. To see how much statistics we have covered this whole year. And I had to laugh out loud when I saw this picture. So I'm going to share my screen, and so I will send you this document, and after we're done here. But this came in on my Instagram feed last night. I'll give credit to whoever sent it. But you've heard me say, "Oh, this isn't too bad." Well, literally, this is kind of a graphic of the whole world of statistics. And this year, we have been here, here, and here. So the good news is, if you're interested, if you really love this class and you want to continue in the field, there's plenty out there. So it's funny how much we've covered, but in the grand scheme of things, how big this field of statistics really is. So I thought I'd share that with you. While most of you are looking at memes of Drake and other things, this is what stats teachers look at, I guess. Oh well, enough of that. Let's get the show on the road here and start talking about our next topic, which we'll call significance tests or hypothesis testing. Both of those things mean the same. And earlier today, I sent you a PDF of these slides, and I wanted you to have them. Some of you may want to print them out and make notes as we go through. But honestly, your textbook does this. I mean, this slides were prepared by the text author, so they go hand in hand, and you can probably follow along pretty well just in the textbook. But there's, especially in this first section, there's so much detail, and it's always been hard for me in class to write these notes. So I've been using these slides, and I think it's helpful. We'll just have to wait and see, I guess. But we'll walk through here and introduce today and tomorrow. Really is the introduction to hypothesis testing and or significance testing. And our goal is to look at evidence provided by the data about a claim concerning a population. And if you remember that very first slide, I should have dug it out, I guess, and maybe tomorrow I'll have it out. But that very first slide where we talk about the population and pulling a sample out of the population, doing some analysis, and then drawing inference. Well, we have now come full circle. We're going to be able to look at data, and we're going to be using that data to assess a claim concerning that population. And the definition of a significance test is it's a step-by-step procedure for comparing observed data with a claim that we want to assess. In other words, we'll collect data, we'll compare that side by side with a claim about the population, and we'll decide Is there enough evidence to reject that claim, or does the evidence is the evidence such that we can't reject the claim? Now, here's the key thing about a significance test. We will never be able to say the claim is true. And we'll get into an example in just a minute. What we will say is that there's evidence to suggest the claim is false, or we will say there's no evidence to indicate that the claim is false. We will never say it's true because we can never be 100% certain. And so we have to be very careful about the conclusions we draw from this significance test. Now, we will be most often looking at the population proportion or the population mean. But that doesn't have to be the case. Any population parameter is fair game for a significance test. We can do a significance test on a standard deviation or a max or a min or any of those parameters that we feel like are important for the data that we're looking at here. And so get that out of the way. We'll take a look at the logic of statistics testing and how to perform them for proportions and means, and we'll see a connection with confidence intervals. The good thing here is that a confidence interval is one way to gather information about a population. A significance test is another way, but the two are really related in a pretty fundamental way. So you might look at it as two sides of the same coin, really. So if we took a lot of random samples and the claim were true, we might get a result like this. Or if the claim is not true, we would rarely see this probability. And so let's just take a look at an example we've used a lot in class with a number of star basketball players in our class this year. We've talked about shooting free throws. So here we have a basketball player that claims his free throw shooting percentage is 80%, meaning in the long run, over the course of the season, he expects to hit about 80% of his free throws. What's going to happen on the next one or the next three? We don't know. Probability in the short run is unpredictable, but over the long run, we expect him to hit about, or her to hit about 80% of his free throws. So we take the basketball player and put him in the gym, put a basketball in her hand or his hand and say, all right, shoot 50. Let's see what happens. And then out of those 50, it turns out in that one sample, he makes 32 of them for a sample proportion p hat of 0.64. So what do we claim? What do we conclude about this claim of being an 80% free throw shooter? Well, that's the whole process that we're going to go through in this chapter. That's kind of the where we're headed. So, well, first of all, what we've been doing up to now is we've been looking at lots and lots of samples taken from this same population. Ideally, we could just have the shooter, the basketball player, shoot 53 free throws 400 times in a row, and then we could record all that data, graph it, do the analysis. But that's a little bit impractical. So often we rely on simulation software to generate that set of data. And if we do that, it might look something like this. Here is the population parameter or the claim of the basketball player Each one of these dots represents one single set of 50 shots. And on the left-hand side here, we see that one particular example, or that one particular sample where he made 32 out of 50 for a p-hat of 0.64. And when we look at it, in that whole set of 400 simulations, only 3 of them were as low as 0.64. And we can say what we have done in the past, what we've done up to this point, we've taken this evidence and the fact that this one dot's kind of out here by itself, really far out in the left-hand tail of this estimated sampling distribution. Because it's kind of a rare event, we would say, you know what, there is evidence against the player's claim that he really makes 80% of his free throws. Well, in this chapter, what we're going to be looking at is a little bit more formal way to attack this problem. How far in this left-hand tail does it have to be before it's really, really unusual? Can we quantify that in some amount? And so that's what this chapter is all about. And so up to now, we would say it's kind of a rare event. In fact, it's a really rare event. And so we think there's evidence, convincing evidence, that the player's claim is not true. So this is the logic. And honestly, this is what we've been doing for the last couple of weeks. What we're going to do in this chapter is we're going to make this more of a step-by-step process with a little bit more quantitative aspect, and not just a qualitative one. Okay, so continuing on with our discussion here, 2 things could have happened in that one particular sample where we got a p-hat of 0.64. Perhaps the basketball player really does hit 80% of his free throws and just had some really bad luck. I mean, all of us have experienced that in one way or another, whether we play basketball or whether we do something else. We've all experienced a run of bad luck, and perhaps that's what explains this. Or perhaps the population proportion is in fact really less than 0.8. Maybe the basketball player doesn't know precisely what his free throw shooting percentage is, and it's not really as high as he thinks. And so the sample is not an unlikely outcome in a population whose proportion is not 0.8. Maybe it's a little bit lower, 0.75 or 0.7, something like that. What we're going to be looking for is outcomes that so rarely happen, if the claim was true, that there is good evidence that the claim is not true. And you kind of have to read that statement over and over again and let it sink in. What we're looking for is an outcome that would rarely happen if a claim is true. There is good evidence that the claim is not true. So if the claim is true, then this data point shouldn't be so rare. But because it is rare, how strong is the evidence that the claim is not true? That's really what we're doing. And so the process is this. We're going to propose 2 hypotheses. And you know what a hypothesis is. You've had science class, and it's a statement that you wish to prove, basically, is a hypothesis. And the claim about the population, we're going to call the null hypothesis. And that's where we start. We're going to claim that we're going to say, okay, we believe this population hypothesis is true And then what we're going to do is propose an alternate hypothesis. And we're going to look to see if this alternate hypothesis, if there is strong evidence for this alternate hypothesis. And if there is strong evidence for it, then we'll have to call into question this original or null hypothesis. And normally this null hypothesis or the original hypothesis is a statement of no difference, or another way of saying that is a statement of equality. For example, in the basketball player's case, well, we'll look at that in just a minute. Here's a formal definition. This text box, something you want to pay attention to. We'll be talking about the null and the alternate hypothesis over and over now for the next several days. The null hypothesis is referred to symbolically as HO, and the alternate one is HA. And so we cannot, the approach we're going to take is we can't prove that this one is true. So what we're going to do is we're going to propose an alternate. And if there's strong evidence for this alternate, then we're going to have considerable doubt about the original one. Okay. So for the basketball player, what we would say, the null hypothesis is the population proportion is 0.8. And our alternate, the thing that we're going to try to prove is that it's less than 0.8, where the population parameter P is the long run proportion of made free throws. Now, this is going to show up in one of the slides. I'm not sure where, but I want to go ahead and start making this point. When we make a hypothesis statement, either the null or the alternate, always use the population parameter. Never use a statistic like p hat or x bar. Always use the population parameter p, or mu for the population mean, or sigma instead of the sample standard deviation SX. Always make your hypothesis statements in terms of the population parameter. Okay. And so the null hypothesis is almost always a statement of equality. Some parameter from the population equals a value. Sometimes that value is equal to 0. Sometimes it's equal to some number like 0.8 in this case. The alternate hypothesis can take one of three forms. Sometimes we're trying to prove that the parameter is less than the particular value. It's less than 0 or less than 0.8 or less than 500. Or sometimes we're looking at it in terms of being greater than a particular value, greater than 0, greater than 0.8, greater than 500, or simply that it is just not equal to that value. That it is some value other than that. It could be either greater than or equal to, it's just not equal to it. So the alternate hypothesis usually comes in three different statements or types of statements. And so we have to kind of dig into the case to figure out what we're talking about. And in this case, take the basketball player, for example. We're going to test that it's less than 0.8 simply because the one data point that we got was so far less than 0.8 at 0.64. If the sample that we had taken and the player hit, say, 46 out of 50, then we might choose the alternate hypothesis that P is greater than 0.8. But in this case, because our one data point is less than that, we'll choose the alternate hypothesis in this form. So we have to kind of take our clue from the case and the context of the case as to where we go. So if we have a greater than or a less than scenario, we're going to call that a one-sided test. If we have a not equal scenario, we're going to call that a two-sided test. And you've heard me refer to one-sided or one-tailed test and two-tailed test. This is essentially the same thing. We're going to be looking at one, if it's a less than or a greater than scenario, we'll be looking at one side of the curve. If it's a not equal to scenario, we'll be looking at data in both tails. And we're going to use symmetry of the curve to help us interpret the two tails. And but for right now, we need to be able to distinguish between a one-sided test where we're looking at a parameter less than a value or a parameter greater than a value, and the two-tailed test or two-sided test where we're looking at it's just not equal to it. It's some value other than what we proposed in the null hypothesis. And so again, here we go. Just a reminder, always use population parameters in our hypothesis statements. Never use the sample statistic, whether that's p hat or x bar or whatever it is. Just always use the parameter. And I think this is I want to go through this example. Yeah. Okay, so we want to conduct a job satisfaction survey of assembly line workers. And the assembly line comes in two forms, or that you can work on the assembly line in one of two ways. You can be machine paced. In other words, a machine is feeding you parts and you're doing your operation and then keeping going, or it's self-paced where you're kind of working at your own pace. So we did the study and we took 18 subjects, 18 people at random from a company with over 200 who put together electronic devices. And you've seen these assembly lines like an iPhone assembly line or something, and there's a long conveyor and people standing on either side. They pick up a widget and they attach something to it and they put it back down and it keeps going. The next one they pick up, that is a machine-paced assembly line, and a self-paced assembly line is the people are working side by side, and I hand something to Elijah and he hands it to Riley, et cetera, et cetera. So you get the idea. So half of the 18 people were randomly assigned to two groups. Here we have an experiment. We are imposing a treatment, and we're dividing the sample group into two groups. They both did similar work. One was self-paced. One of them was machine-paced. They did that for 2 weeks and took their test of job satisfaction. And then they switched roles and took the test again after 2 more weeks. So we have 2 survey results here. And in this case, the response, the thing that we're looking at here is the difference in the scores. And we're going to interpret it self-paced minus machine-paced. That's the difference that we're looking at. We could look at it machine-paced minus self-paced, but when we're doing a difference, we have to pick one and then we have to stay with that one the whole time. We can't just we can't just switch back and forth. So we're going to create this response variable, or this new random variable called the difference between the self-paced and machine paste. So let's do this. Let's describe the parameter of interest in this case. And it's the mean of the differences. Sometimes you might hear it in terms of the difference in the means, because we'll calculate a mean in each one and then we'll take the difference of the job satisfaction scores and the population of all assembly line workers. Okay, so we took a sample of 18, but our population of interest is everybody in the company. We want to use this sample of 18 people to gauge the satisfaction of everybody that works on an assembly line in this company. Okay, so for now, what we want to do is state the appropriate hypothesis for performing the test. So we want to describe the null and alternate hypothesis. Okay. So we want to see if their job satisfaction is different. So what we want is, we are going to start out with, hey, we believe it's the same. We think that the job satisfaction is going to be the same value whether you're machine paced or self-paced. So we think that difference is going to be equal to 0. And what we're going to set out to prove is that that the mean is not equal to 0. And right now, we don't have any data. We'll talk about that tomorrow. I really just want us to look at this scenario of correctly stating the null and alternate hypothesis, because honestly, this is more than half of the work right here, is making sure that you get this part set up correctly. If you make a mistake here, you're going to be walking down the wrong road from the very beginning, and it'll be really, really, really hard to recover. So as we go forward, the ability for you to make the correct null and alternate hypothesis claims is going to be really, really important. And yeah, we're going to stop here for today. What I want us to do now as a group is take a look at your textbook on page 546. So dig out your textbook to page 546. And we're going to go over some of these examples at the very beginning. Let me get situated here. Not going to do any calculations today. There'll be plenty of time for that. We'll do our calculations later. But I do want you to be able to see how we put these things together. If you don't have your textbook handy, that's fine. I'll read each of the questions, and then we'll just kind of go through these together. All right. So let me bring back the the screen. Okay. So question number 1 here, about lefties. Simon reads a newspaper report claiming that 12% of all adults in the United States are left-handed. He wonders if 12% of the students in his large public school, high school, are left-handed. So he chooses a simple random sample of 100 students and records whether or not each student is right or left-handed. So what we're trying to do here in the instructions up above, it says we want to state the appropriate null and alternate hypothesis. And then we want to define the population parameter that we're interested in. So we're looking at lefties here. And so let me just ask the group here. Does anybody want to make a guess as to what the null and alternate hypothesis might be? We're not there yet. Okay. Well, let's do this. The claim from the newspaper was that 12% of U.S. adults are left-handed. So our original or null hypothesis is that P is equal to 12% or 0.12. And so the alternate hypothesis is that P is going to be something different from that. And so what we have to decide is P going to be less than, is P going to be greater than, or P going to be not equal to? Those are the three choices we have here. And in Simon's case, it could be that he has more than 12% students at his school that are left-handed. It could be that he has less than 12%. We don't really know. So the best alternate hypothesis to use here is that since we don't have an idea as to whether it should be less than or equal to, we're just going to say that it is not equal to, and we'll do a two-sided test. Now, don't worry about what that is yet. We'll learn about what two-sided tests are soon enough. But the alternate hypothesis in this case is simply that the proportion of left-handed students is not equal to 0.12, where P is defined as the proportion of lefties in his school, let's say high school. Yeah, in his high school. Okay. So that's it. That's all we're after right now, to be able to correctly state the null and alternate hypothesis and make sure we clearly understand what population parameter we're talking about. Let's do another one. Number 2, don't argue. The context is this: a Gallup poll reported a national survey of 1,028 teenagers revealed that 72% of teens said they seldom or never argue with their friends. Okay. I guess I have my own opinion after raising 2 teenagers, but anyway, we'll say this is the survey and this is their result. And Yvonne wonders whether this national result would be true in her large high school. So she does a survey, a simple random sample survey of 150 students at her high school. Okay. So again, we want to identify the null and alternate, I keep saying alternate hypothesis. Anybody ready to take a stab at that one?
P is equal to 0.72.
P is equal to 0.72. I guess you're saying that's the null hypothesis, right? Because that's what our
Yeah, yeah.
okay. So what would be
And then
the alternate?
P is not equal to 0.72.
P is not equal. That's right. We don't have any evidence to suggest that that the number of or the proportion of students in her high school that argue with their friends is more or less than this value. So we're going to have to look at it as simply not equal to. And then what is P defined as?
Proportion of friends, I don't of friends who don't argue in her school.
That's it. Proportion of friends who who say they don't or don't ever or seldom or seldom ever, I think, to be complete, seldom ever argue in her high school. Again, the population, it's important that we identify the population is her high school, whereas the claim came from a national study. The proportion that Yvonne is interested in is the students in her high school. Well done. I've got to be honest. This is probably the hardest part of this whole section. Well, I don't know if it's the hardest, but it is really hard to get started here. And for example, let's just say we said, oh, we think the alternate hypothesis should be this. Then we're going to go down a testing path, an analysis path that ignores the other tail. And so there are lots of opportunities for us to make a pretty big mistake here if we don't get this part correct to begin with. Okay. And so we'll do one more. We'll look at number 3. And this one is a national study of attitudes towards school. So this one is titled Attitudes. So let's read through the case. The survey of study habits and attitudes is a psychological test that measures students' attitudes towards school and study habits. How many of you want to take that one today? The scores can range from 0 to 200. The mean score for U.S. college students is about 115. A teacher suspects that older students have better attitudes towards school. So she gives this survey of study habits and attitudes to a simple random sample of 45 of the over 1,000 students in her college who are at least 30 years of age. Okay, so an older student here is defined as somebody who's at least 30, so 30 or over. And we want to identify the null and alternate hypothesis here. So what do we think? What do we think the null hypothesis is? Anybody want to give it a go? Well, in this case, we're not looking at a proportion. The parameter we're looking at is the mean score. And in this survey, or in the somehow we know that the mean for college students is about 115. Not really clear how we know that here, but that's not important. We're going to use this as our baseline, And then we're going to compare that to the mean being what? Less than, greater than, or simply not equal to 115. Anybody want to give me a guess here?
Not equal to?
Well, we could go with that, but what did the teacher think? She suspects that older students have better attitudes. Attitude is better. What do you think the score is going to be?
Greater than?
Higher or lower than that?
Higher.
It's going to be higher. So in this case, we're going to test the claim whether the mean is greater than 115 rather than it's simply not equal to. Because if we tested the claim that it was not equal to, then our conclusion would be maybe it's worse, maybe it's better. We don't know. We just know that it's not equal to 115. What we're interested in is do these older students have a better attitude than younger college students? So we want to go after the alternate hypothesis that the mean is actually greater than 115. And in this case, our population is the mean score on the, and I'll just use the abbreviation SSHA survey for students whose age greater than or equal to 30 at her, does it say, at her college, at the teacher's college. Okay, so the population we're interested in here is students whose age is greater than or equal to 30 in this particular college. That's who we're targeting for the population here. Okay, any questions? Well, what I want to do right now is I'll stop here with these examples and I'll ask you to do for today number 4, 5, and 6. It's the same thing. You've got a case in front of you. You're going to give me what you think is the null and the alternate hypothesis. Hopefully by the end of the year, I'll start saying alternate every time. And then you're just going to define what the population is. So pretty straightforward. It's not calculation intensive at all. Shouldn't be very rigorous. But don't discount the importance of getting this part right. Because honestly, if you get off track here and you make the wrong alternate hypothesis claim, then your test procedure is going to be completely different and you'll draw the wrong conclusion. So it's important that we get started on the right foot. That's why I'm going to take this a little bit slow, make sure we get this correct. And probably for tomorrow, we'll start with a few more examples. And I'll kind of expect you to jump in and give me what your thoughts are here. And then we'll go on to actually testing a claim and understanding what this significance claim is all about. But for right now, I just want to make sure that we can walk before we run here. Okay? Any questions? All right, guys, we'll sign off here and I'll see you tomorrow. Good luck. And if you have questions, feel free to reach out. I'm here. We'll see you tomorrow. Same time, same channel.
Bye.
Have a good, take care.